This video is an introduction to Linux network namespaces. I'll start with a brief definition. Then I'll jump into two examples of using namespaces. I'll walk through two lab-like scenarios that I believe will help make the video more practical. You have the option to simply watch the video, or you can try the same setup on your own system at home. The first example will mimic how Mininet network emulation handles hosts. The second will mimic how OpenStack provides DNS services to tenants. The steps I take are all on a single VM running Ubuntu 14.04 with Open vSwitch and the DNS mask service installed. References. Here is a list of references and recommended resources related to this video. Links to these references are in the video description. The Network Namespaces man page, openvswitch.org, mininet.org, a presentation on Mininet done at Stanford by Bob Lance and Brian O'Connor, docs.openstack.org, specifically the Neutron documentation, and finally opencloudblog.com's many Linux networking blog entries. What are Linux network namespaces? Network namespaces allow there to be multiple isolated network environments running on a single physical host or a single virtual machine. Each isolated network environment has its own interfaces, routing tables, forwarding tables, and network security isolation. Processes can be dedicated to an individual network namespace to separate them from other namespaces. Network namespaces are used in OpenStack, Linux containers, Docker, Mininet, and more. Background on Mininet. The first example using namespaces mimics what Mininet does automatically. However, we will do it in a manual way to learn about network namespaces. If you're not already familiar with Mininet, here is a brief explanation. Mininet software allows you to launch custom virtual network topologies, all within a single virtual machine or a single physical host. Its range of applications includes learning, testing, and teaching about software-defined networking, as well as networking in general. For more detail about Mininet, you should go to mininet.org. You can also watch my Introduction to Mininet video on my YouTube channel. For the purposes of this video, I'll mimic what Mininet does to emulate the simplest topology. This topology will have two hosts connected together through one instance of Open vSwitch. This is done on my single VM. The two emulated hosts will have their own network environment thanks to network namespaces. This setup was demonstrated in a presentation by Bob Lance and Brian O'Connor at a Stanford network seminar, which I'll link to in the video description. The root network namespace. We start with taking a look at the root namespace. This is just the default network environment you see when working on a Linux system. This will be kind of like our canvas that we're going to put our virtual network on top of. So there's nothing new here yet. We will just take a look at my VM's root network namespace before adding new network namespaces. To look around, I will use some iproute2 based commands. This is instead of using the older nettools based commands like ifconfig, route, and arp. So in the standard root namespace, iplink shows there is just a loopback interface and an eth0 interface. IP address, or just IPA, shows the eth0 interface has an IP address of 192.168.1.102. IP route displays the routing table. Adding network namespaces. Now let's add two new network namespaces. Each of these namespaces will represent a single host in our network topology. IP netns add red. IP netns add green. I've just added two new network namespaces named red and green. IP netns by itself displays those two new namespaces. Also, if we look in the directory /var/run/netns, we can see the namespaces listed there as well. If we wanted to delete a namespace, we'd say del for delete instead of add. I won't delete the new network namespaces here though. Looking at the logical diagram now, we have the two new network namespaces red and green. Red and green's network environments are isolated, both from each other and from the root namespace. To look further, we can use the ipnetns exec command. So ipnetns exec red IP link. With this command we are simply running the IP link command. However, instead of running this in the root namespace, we are executing it directly in the red namespace. In red, there is only a loopback interface, and it is down. Checking green as well shows the same situation. IP netns exec green IP link. To emulate a simple network in a manner like Mininet does, we want to connect these namespaces into a virtual switch. In this case, we will use Open vSwitch. Our instance of Open vSwitch will be in the root namespace. OVS vskettle or vsctl add-br ovs1. This starts a new virtual switch that I've named ovs1. By the way, if you'd like more background about Open vSwitch, I recommend going to openvswitch.org. Also, you can watch my Introduction to Open vSwitch video on my YouTube channel. So we now have ovs1. We can check that with ovs-vskettle show. IP link shows that in the root namespace, the interface ovs1 has been added. Checking the diagram again, now we have the two namespaces red and green, as well as our Open vSwitch instance ovs1. Next is to connect all these together. Virtual Ethernet interfaces. To connect the two namespaces red and green to ovs1, we will use VETH pairs, or Virtual Ethernet interfaces. VETH pairs act like a pipe. Anything that goes in one end of the pipe simply comes out the other end. We can use VETH pairs to cross network namespaces. IP link add eth0-r type VETH peer name VETH-r. This IP link command creates a VETH pair. One end of it I am choosing to name eth0-r. This end we are going to put into the red namespace. The other end of our new VETH pair I've named VETH-r. This end we will connect to our OVS instance in the root namespace. What has happened now is there is this VETH pair which can be visualized as a pipe. At the moment, we haven't connected the two ends of it to anything. With IP link, we can see both ends of the VETH pair sitting in our root namespace. We want to connect one end of this pipe to the red namespace, and the other end to our Open vSwitch instance. IP link set eth0-r netns red. This command places the end named eth0-r into the red namespace. IP link shows we can no longer see the interface eth0-r in the root namespace. That is because it is now in the network isolated red namespace. Let's run the command IP link in the red namespace. IP netns exec red IP link. Here we can see the end of the VETH pair we named as eth0-r is now located in the red namespace. Now, let's connect the other end of our VETH pair to OVS. OVS vskettle add port ovs1 VETH-r. This OVS-vskettle command attaches the other end of the VETH pair named VETH-r to OVS1. Running OVS vskettle show, we can see there is a VETH-r attached to OVS1. Now we have the red namespace connected to the OVS instance. The same thing will be done for the green namespace to connect it to OVS as well. IP link add eth0-g type VETH peer name VETH-g. This creates another new virtual Ethernet pair or VETH pair. One side is named eth0-g, the other side is named VETH-g. IP link set eth0-g netns green. This puts the end named eth0-g into the green namespace. OVS vskettle add port ovs1 VETH-g. This attaches the end named VETH-g to OVS1. Now the two namespaces have a path to each other via Open vSwitch. Configuring interfaces in network namespaces. Now that everything is connected together, we need to turn all the interfaces up, and we need to assign IP addresses. Let's start with the link to the red namespace. One side of this VETH pair is on OVS1. However, it is down. I'll turn it up with IP link set VETH-R up. Now we need to work inside the red namespace and execute IP link commands there to turn up loopback0 and eth0-r. IPNetS exec red IP link set dev L0 up. IPNetns exec red IP link set device eth0-r up. eth0-r needs an IP address. IPNetns exec red IP address add 10.0.0.1/24 dev eth0-r. This assigns the IP address 10.0.0.1/24 to eth0-r. IPNetns exec red IPA shows the two interfaces. They are up, and the expected IP address is assigned. IPNetS exec red IP route shows the red namespace now has a route for 10.0.0/24 via its interface eth0-r. Back in the root namespace, running IP route shows the root namespace doesn't have any awareness of 10.0.0.0/24. This is as expected, since the routing of the red namespace is isolated from the root namespace. Now we will do the same procedure for the green namespace, except we'll want to assign 10.0.0.2 for it. IP link set device VETH-G up. This turns up the end of the VETH pair attached to OVS1. Now I'll show a bit of a shortcut. To work inside the green namespace, instead of using the IPNetns exec green command over and over, we can simply start a bash shell within the green namespace. IPNetns exec green bash. Now we are in the green namespace instead of the root namespace, and can use regular IP commands. We no longer have to preface every command with IPNetns exec green. IP link set dev LO up. IP link set dev eth0-g up. These commands turn up the interfaces loopback0 and eth0-g in the green namespace. Finally, we assign the IP. IP address add 10.0.0.2/24 dev eth0-g. Now the eth0-g port has IP 10.0.0.2, which you can see with IPA. Remember that we are working directly in the green namespace since we ran IPNetns exec green bash. So to get back to the root namespace, we would just type exit. Final state. The final state is there are two network namespaces, red and green. In the root namespace is an OVS instance named OVS1. The green and red namespaces are linked together to OVS1 through VETH pairs. OVS1 acts as a layer 2 switch enabling connectivity between the two namespaces. We can confirm connectivity between red and green with a ping. Ping 10.0.0.2. The end result here is we have two emulated hosts connected through Open vSwitch. We could continue this experiment and connect our OVS instance to an SDN controller. However, for our purposes here, which is learning about network namespaces, we will leave it at that. Now we will move on to our second scenario. This one is related to OpenStack. We will connect network namespaces without using VETH pairs, and we will run processes within network namespaces. DHCP and OpenStack. OpenStack is well known as a popular open source platform to deploy cloud infrastructures. Here we will mimic one small piece of OpenStack, providing DHCP services to tenants in the cloud. In the cloud, we have individual physical nodes that are responsible for providing many DHCP processes, one for each virtual network of every tenant. When we have all these DHCP processes running on individual hosts, these processes need to be isolated. We can use network namespaces for that isolation. To mimic this behavior from OpenStack, we will build on the previous Mininet example. Keep in mind that in a real OpenStack deployment, there would be a hypervisor like KVM and real VMs versus our emulated hosts. So we start with the two namespaces red and green, which are emulating two hosts. VLAN separation. First, the two namespaces red and green will be isolated from each other. In this scenario, red and green will represent two different tenants in the cloud. Since they are both connected to the same Open vSwitch instance, VLANs will be used on Open vSwitch to keep them isolated. OVS vs kettle set port vth-r tag equals 100. OVS vs kettle set port vth-g tag equals 200. These OVS vs kettle commands changed VLANs on the two ports connecting to the two namespaces. The first one moved port vth-r to VLAN 100. The second one moved vth-g to VLAN 200. Looking at the updated diagram, we see the namespaces are now isolated by VLANs. Also, we want to remove the current network namespace IP addressing, since we will use DHCP instead. IP netns exec red IP address del 10.0.0.1/24 dev eth0-r. IP netns exec green IP address del 10.0.0.2/24 dev eth0-g. These commands are executed in the respective namespaces and remove the configured IPs. Add network namespaces. Now I'll add two new network namespaces. These will host the DHCP processes for our two tenants. IP netns add DHCP-r, IP netns add DHCP-g. The first namespace DHCP-r will be used for the red tenant. The second one, DHCP-g, will be used for the green tenant. Open vSwitch internal ports. Earlier, to connect red and green to Open vSwitch in the root namespace, we used vth pairs. For DHCP-r and DHCP-green namespaces, we will connect through Open vSwitch internal ports. First, let's work with the connection to DHCP-r. OVS vs kettle add port OVS1 tap-r. This creates a new port named tap-r on OVS. OVS vs kettle set interface tap-r type equals internal. This makes this new port an internal port. OVS vs kettle set port tap-r tag equals 100. This places the port into VLAN 100. Let's set up the port for green. OVS vs kettle add port OVS1 tap-g, creating the port named tap-g. OVS vs kettle set interface tap-g type equals internal, making the new port of type internal. OVS vs kettle set port tap-g tag equals 200, putting the port in VLAN 200. OVS vs kettle show confirms our configuration so far. There are the two new internal ports named tap-r and tap-g in VLANs 100 and 200 respectively. Looking at the diagram, there are two new internal ports. However, they are sitting in the root namespace still. They need to be moved to the right namespaces. IP link set tap-r netns DHCP-r. This command moves the port tap-r into the DHCP-r namespace. IP link set tap-g netns DHCP-g. This command moves the port tap-g into the DHCP-g namespace. IP link in the global namespace confirms we can no longer see DHCP-g and DHCP-r since they've been moved. Even though we can't see the ports in the root namespace, we can still see them on OVS. OVS-vsctl show. And here is the updated diagram. Interface configurations. Now we will turn up interfaces and assign IPs in the new namespaces DHCP-r and DHCP-g. Let's go directly into the bash shell for the namespace DHCP-r with ipnetns exec DHCP-r bash. IP link set dev lo up. IP link set dev tap-r up. Turning up the loopback interface and the tap-r interface in the namespace DHCP-r. IP address add 10.50.50.2/24 dev tap-r. Now 10.50.50.2/24 has been assigned to interface tap-r in the DHCP-r namespace. We will do the same for DHCP-g. IP netns exec DHCP-g bash. IP link set dev lo up. IP link set dev tap-g up. IP address add 10.50.50.2/24 dev tap-g, and adding IP address 10.50.50.2 to the tap-g interface in DHCP-g. Note here how I intentionally used the exact same IP addresses in the two namespaces DHCP-g and DHCP-r. This is to demonstrate that these two environments are isolated from one another and don't interfere. This is what one would expect in a cloud environment. We want each tenant to use any private IP addressing they care to use, and for it to be isolated from other tenants. Overlapping IPs are fine due to the isolation provided by network namespaces and VLANs. Running a process in a network namespace. Finally, we want to run DHCP. For DHCP, we use the DNS mask service. We want to have two DNS mask services running, one for the red tenant and one for the green tenant. These need to be isolated from one another. Therefore, we use the ipnets exec command yet again. ipnets exec DHCP-r DNS mask --interface equals tap-r --DHCP-range equals 10.50.50.10, 10.50.50.100, 255.255.255.0. This starts DNS mask, but within the DHCP-r namespace. DNS mask runs on the tap-r interface and uses a pool in this range. Now the exact same command again, except it is in the DHCP-g namespace. So we'll make those changes here. I've now started two DNS mask processes that are using the same range of IPs for a DHCP pool. However, they are isolated from one another. The first process is running in the DHCP-r namespace, the second in the DHCP-g namespace. We can actually validate this by the process IDs. PS-EF shows PIDs 3162 and 3165 for the two DNS mask processes. IPNetNS identify 3162 shows process 3162 is in the DHCP-r namespace as expected, and IPNetNS identify 3165 shows that the PID 3165 is in the DHCP-g namespace, also as expected. Let's see that this all worked all right by pulling IPs for our clients. First, for the red namespace, IPNetNS exec red DH client eth0-r. This seems to have completed. IPNetNS exec red IPA shows we indeed have received an IP address assigned by the DNS mask service for the red tenant. Now the same for the green tenant. Again, we see this has worked. One last check of the diagram to see that DNS mask is now running in two different namespaces, and our emulated tenants red and green were able to receive IP addresses by isolated DHCP processes. Final review. I'll close now with a final review of what has been discussed. This should help solidify all the concepts we walked through in this video. Before that final review, a request for you, the viewer. If you found this video to be helpful, please subscribe to this channel for more like it. Also, to contact me directly, I can be found at linkedin.com/in/David Mahler. Review. This video covered Linux network namespaces and described some ways they can be used. First, we mimicked how Mininet builds emulated network topologies. We created two isolated network namespaces, red and green. We created virtual Ethernet or VETH pairs to connect these namespaces through an OVS instance running in the root namespace. We turned up interfaces and assigned IP addresses in the namespaces. Then we demonstrated reachability between red and green. We also saw that the root namespace had no knowledge of the layer 3 addressing used by the network namespaces. After this, we mimicked how OpenStack provides DHCP services to tenants in the cloud. We turned our namespaces red and green into isolated environments by assigning VLANs on the OVS side of the VETH pairs. Then 2 new namespaces were created to host 2 isolated DHCP processes. These namespaces were connected to OVS by creating OVS internal ports, moving those ports to the appropriate VLANs, and finally by moving these ports directly into respective namespaces. Lastly, it was demonstrated that the tenants were able to acquire IP addresses from separated DNS mask processes running in individual network namespaces. That wraps up this video, and thank you for watching.